Hello, today we will start the study of monotonicity of function. We know that a function is a mathematical model that describes the law of changes in things. We can learn about the law of changes in the objective world by studying the nature of a function. So what is the property of function? In general, the nature of a function is the invariance and regularity in change. To study the properties of functions is to learn to find laws in motion changes. Please review the primary function, quadratic function, and inverse proportional function that we learned in junior high school. How do we study their properties? We study the properties of functions through images. So please look at the graphs of these functions. What laws can you find in the changes? Everyone's answer involves many different aspects, such as the characteristics of lifting changes, the characteristics of symmetry, and the characteristics of the highest or lowest point. Now, we will focus on the characteristics of the image from left to right. Let's see the first figure. It rises from left to right, so in the interval from negative infinity to positive infinity, y always increases with the increase of x. Let's look at the second function. On the two intervals of negative infinity to negative 1 and 0.2 to 1, the rising y of the image from left to right increases with the increase of x. On the two intervals of negative 1 to 0.2 and 1 to positive infinity, the decreasing y of the image from left to right decreases with the increase of x. This is the property of function that we will study together today. On the basis of learning in junior high school, we should use quantitative methods to describe the change law of function value increasing or decreasing with the increase of independent variable, which is the monotonicity of function. In junior high school, we studied quadratic function. Now we take the quadratic function y equals x squared as an example. We know that y decreases with the increase of x. How do you understand the statement that y decreases with the increase of x? Can you talk about its quantitative characteristics? In order to make you think better, I would like to further remind you. When x increases, how can I use symbolic language to express this sentence? How can the corresponding function value y decrease be expressed in symbolic language? Please observe this table. Can you give a specific description? We describe it from a numerical point of view. For example, when x increases from negative 5 to negative 4, the function value fx decreases from 25 to 16. For example, when x increases from negative 4 to negative 3, the function value fx decreases from 16 to 9. For example, when x increases from negative 3 to negative 2, the function value fx decreases from 9 to 4. Can you write down all the changes? Obviously, this process cannot be completed one by one, because it is infinite. Can you summarize the common points of the above specific numerical changes with the help of alphabetic symbols? We can sum up the above changes with alphabetic symbols. As long as x1 is less than x2, fx1 is greater than fx2. What are the requirements for the two independent variables x1 and x2? Only certain numbers from negative infinity to 0 can be used for x1 and x2. Can you give an example of your point of view? It is found that it is obviously not enough to learn only x1 and x2 values of certain segments. We can find that when a is smaller than b and fa is larger than fb, but it is obvious that y does not always decrease with the increase of x in the b interval a to b. So it is obviously not enough to take only some x1 and x2. How should we take them? Some students said that since some are not enough, we will take all x1 less than x2 and fx1 greater than fx2. So how can we explain all this? It is still an infinite concept, and we still cannot operate one by one, but what quantifiers can we use to replace all? Can you express it strictly? We can replace everything with anything. That is to say, if x1 is less than x2, fx1 is greater than fx2. Then I have another question. Maybe some students have this question. Why is fx1 larger than fx2 here? At this time, it is necessary to prove the value ratio of two functions, which is essentially an algebraic proof of inequality. Later, we will do a strict proof together. So just now we have described the monotonicity of the function y equal to the square of x on the negative infinity to 0 in symbolic language. Now can you imitate the above method and give a symbolic language description that y increases with the increase of x on the interval 0 to positive infinity? Either x1 or x2 should be taken from the interval 0 to positive infinity. As long as x1 is less than x2, fx1 is also less than fx2, which indicates that y increases with the increase of x. Okay, please do another exercise. Please imitate the above process and use strict symbolic language to describe the monotonicity of function y equal to negative x squared. Take any x1, x2 from negative infinity to 0. As long as x1 is less than x2, fx1 is also less than fx2, which indicates that y increases with the increase of x. While in the interval 0 big positive infinity, take any x1, x2. As long as x1 is less than x2, there will be fx1 larger than fx2, which indicates that in this interval, y decreases with the increase of x. So just now we have studied how to express the monotonicity of two functions in symbolic language. Now, can you summarize the characterization methods of the monotonicity of these two functions and give the symbolic representation of the monotonicity of function y equals fx on interval d? Let's look at the definition together. Generally, let the definition field of function fx be I, and the interval d is contained in I. If any x1 and x2 belong to d, and if x1 is less than x2, there is fx1 less than fx2, then the function fx is said to be monotonically increasing on the interval. In particular, when the function fx increases monotonically in its domain, we call it an increasing function. So everybody, can you give the definitions of monotone decreasing and decreasing functions by analogy with the definitions of monotone increasing and increasing functions? From the definition, it can be seen that only any x1, x2 in the definition belongs to D. When x1 is less than x2, it is changed to have fx1 greater than fx2, then the function fx is called monotonically decreasing in the interval. In particular, when the function fx decreases monotonically in its domain, we call it a subtraction function. Now we have clarified the definition of monotonicity. Everyone, can you give examples of monotonic increasing and increasing functions in the whole definition field? Can you give an example of a function that monotonically increases on some intervals in the domain, but monotonically decreases on others? We all give examples of our own functions. For example, let's see that the primary function y equals x plus 1. On its field R, y always increases with the increase of x, so it is an increasing function on R. However, the quadratic function y we just studied is equal to the x squared. It is monotonically decreasing in the interval from negative infinity to 0, while it is monotonically increasing in the interval from 0 to positive infinity. Therefore, it has two different monotone intervals, but it is not a monotone function in the definition field. Through examples, we hope you can understand that monotonicity is a local property of a function for an interval in the definition domain. To describe the monotonicity of a function, we must say which function is in which interval and how monotonic it is. We allow functions to increase monotonically on some intervals, but decrease monotonically on others. But please note that only monotonically increasing in the entire domain can we call it increasing function. Similarly, only monotonically decreasing in the entire domain can be called a subtraction function. It should also be reminded that when a function has multiple monotone intervals, union cannot be used at will. For example, if the function y is equal to 1 over x, we can't say that it is infinitely 0 and monotonically decreasing compared with infinity, because we can find the antonym that negative 1 is less than 1, but f negative 1 is also less than f1, which makes it not meet the definition of monotonically decreasing in the field. So we can only say that the function y is equal to 1 over x, decreasing monotonically on the open interval from negative infinity to 0 and on the open interval from 0 to positive infinity, respectively. Well, now we will prove the monotonicity of some simple functions by using the definition of monotonicity. First of all, let us look at example 1. According to the definition, we study the monotonicity of the function fx equal to x plus b, where k is not equal to 0, that is, we study the monotonicity of a function. Before proving, I would like to give you two tips. First, to study the monotonicity of a function, we need to use the definition of monotony to examine which regions within the definition domain are monotonically increasing and which regions are monotonically decreasing, and to clarify the scope of study. Secondly, the specific operation method is to investigate the size relationship between fx1 and fx2 under the condition that x1 is less than x2. The ratio can be made worse by using the properties of inequality and algebraic distortion. We shall prove together, first of all, that the function fx is equal to x plus b, where the domain of k is not equal to 0 is R. Then from the graph of the primary function, we know that the primary function should be monotonically increasing or monotonically decreasing in the domain of definition. So we take either x1 or x2 in the domain R and specify that x1 is less than x2. Then, by subtracting the value of the function, fx1 minus fx2 is equal to kx1 plus b minus the bracket kx2 plus b. The reduction gives k times x1 minus x2. Since we specify that x1 is less than x2, x1 minus x2 is less than 0. At this time, we will discuss the sign of this formula and the positive and negative of k. When k is greater than 0, k multiplied by x1 minus x2 is less than 0. So fx1 minus fx2 is less than 0. Thus, fx1 is less than fx2, and the first-order function is an increasing function. When k is less than 0, multiplying k by x1 minus x2 is greater than 0. So fx1 minus fx2 is greater than 0. So fx1 is greater than fx2, and the linear function is a decreasing function. Therefore, we prove that for a linear function, when k is greater than 0, it is an increasing function, and when k is less than 0, it is a decreasing function. We obtained this conclusion using a graph of a linear function when we were in junior high school, and here we further proved it using rigorous reasoning operations, making the conclusion even more rigorous. Here, comparing the size of fx1 and fx2 will be converted to comparing the size of fx1 minus fx2 and 0. This approach embodies the idea of simplifying complexity and making difficult things easier in mathematics. Let's take a look at the second example again, which is a physics problem. Will's law in physics states that P is equal to K2V, where K is a normal number. Tell us that for a certain amount of gas, as its volume V decreases, the pressure P will increase. Try to prove this with the monotonicity of the function. Please think about the meaning of the phrase when the volume decreases slightly, the pressure P increases. If we consider V as the independent variable and P as the function value, that is, as the independent variable decreases, the function value will increase. So we only need to prove that the function t is equal to k compared to v, where v belongs to the open interval and 0 to positive infinity is the subtraction function. Let's prove together. First, take v1 and v2 in the open range from 0 to positive infinity in the domain, and specify that v1 is less than v2. Subtract the function values, p1 minus p2 equals k minus v2, and the integral is equal to k multiplied by v1 minus v2 divided by v2 minus v1. Since v1 and v2 are taken in the open range from 0 to positive infinity, v1 multiplied by v2 is greater than 0, and since v1 is less than v2, v2 minus v1 is also greater than 0, and k is greater than 0 for all three factors, so p1 minus p2 is greater than 0, so p1 is greater than p2, since we assume that v1 is less than v2 and p1 is greater than p2, according to the definition of monotonicity of the function. The function p is equal to k compared to v, where v belongs to the open interval and 0 to positive infinity is the subtraction function. When the volume v decreases, the pressure p will increase. Example 2 is a formula in physics from which we can understand that function models can be used to describe phenomena in the real world. The study of mathematics aims to abstract a type of motion and change phenomenon into a type of function, and obtain the laws of change of things by studying the properties of this type of function. Can you summarize the basic steps for proving the monotonicity of a function on an interval using the definition of monotonicity based on the proof process of example 1 and example 2? Let's summarize together. The first step is to take the values x1 and x2 of any two independent variables in the interval and specify that s1 is less than s2. Step 2. Calculate fx1 minus fx2 and decompose fx1 minus fx2 into several equations that can directly determine the sign. Step 3. Determine the sign of fx1 minus fx2. If fx1 minus fx2 is less than 0, then the function fx monotonically increases on the interval, while if fx1 minus fx2 is greater than 0, then the function fx monotonically decreases on the interval. Finally, let's review the content of this lesson. Please think about the following questions. Firstly, what is the monotonicity of a function? Can you provide some specific examples? I hope everyone can further understand the definition of monotonicity through examples. Secondly, what key issues should be addressed when proving the monotonicity of a function? It is important to note that the interval for studying monotonicity should be determined first, and then any value where x1 is less than x2 should be used to compare the difference between fx1 and fx2. Prove using the definition of monotonicity. Thirdly, based on the learning process of this lesson, what is your understanding of the research methods for function properties? We study the monotonicity of functions through methods such as visual representation, qualitative description, and quantitative characterization. This is also a general approach for our future research on the properties of other functions.